with this one?
Right.
Right. We'll take care of it. Okay. Thank you.
All right.
Thank you. Sorry for it. Okay, so again, we said we have some innovation over the years and things like that, but we like to tell you that this concrete we are using is a very durable material. How do we know that? Because we know that Romans have masters of concrete, have this beautiful structure, for example, Pantheon, and it's about 2,000 years old. So there is the longevity associated with Pantheon. And we know that if we design it and build it right and keep concrete dry, it will last forever. So we know that it is a material that has durability as an important characteristic. Now, what we find out in real life is that when we have infiltration into concrete, now it's no longer dry, things are penetrating into concrete. If we have, for example, water and solutions penetrate into concrete, then we would have some problems, some distress mechanisms. How do solutions get into concrete? They get into concrete through the poor quality concretes, the permeability concept of the concrete, and also through the cracks. If the cracks are wide, then they will let in the solutions. So it's important to keep the cracks tight, and we'll talk a little bit about that. So what are these deterioration mechanisms that we face? One of them is a physical issue, freezing and thawing. As we know, as the water freezes, it causes some issues. Another one is alkali aggregate reaction. Another one is sulfate attack, and also corrosion. Corrosion is if there's reinforcement in the system. So let's look at these. As you see on the freezing and thawing, this structure is in Virginia, but was made at the time that they were not using air entrainment. So now we can put some air entraining admixture into the concrete and avoid such distress in our concrete. And how does this happen? Why does this happen? When we are in a hurry and put our bottle, drink bottle, glass bottle into the freezer, and then forget it there and come back, we find that water bottle is broken. And the reason is that water expands 9% upon freezing. So that's an issue for us. Same thing happens if concrete gets saturated, and if that freezing takes place, there will be very high pressure, hydraulic pressures occurring, and that may break that concrete. So what do? We entrain small bubbles in the concrete. So the next one here on the right is the alkali silica reaction. This is a median. And as you see, I took that picture. As you see how what happened to that concrete because of a reaction between the siliceous aggregates. Some of them are more reactive than others. And then the alkali is mainly coming from the cement. It forms a gel, and that gel expands. And then sulfate attack. And we also know that the sulfate and works with some of the hydration products in the system and causes a calcium sulfoaluminate, which is an expensive product. So it's an expensive, it needs space. It doesn't have any space, it's a rigid system, so it cracks. And here is the corrosion. In the corrosion, as you know, the corrosion product, which is the rust, takes a larger volume. So it tries to expand and cause cracks and spalling in the system. So these things do happen, but fortunately, we know how to take care of them. Okay, so how can we then keep our concrete dry? Don't let things penetrate into this. And that's one way of protecting them. But there are other ways of protecting them by looking at the ingredients and the proportions in the concrete. We can also do some good things to our system. But one of them, very effective one, is if we can keep concrete dry. Don't let things penetrate into the concrete. So how do we do this? By reducing the permeability of the concrete. And this is mainly done by using the supplementary cementitious materials, such as fly ash, fly ash as we use in the States, or the slag cement, and silica and metakaolin. These are all siliceous materials that we can add to concrete. And then low water cementitious materials ratios. As you know, our specifications usually has a maximum limit, which we don't let to exceed. We don't want to exceed because of durability reasons. And then the other bullet that you see there is crack control. We like to have tight cracks. We know that if we get tight cracks, meaning that less than 0.1 millimeter. To give you an idea what 0.1 millimeter is, it is the thickness of the hair. It's a very small dimension. And we know, for example, in VDOT that we can fill cracks that are larger than 0.2 millimeter. So now I'm talking about cracks that are so narrow type of thing. And we are able to do that. Okay, so if we keep those cracks so tight, things cannot penetrate into it. And how we do that, definitely we look at the ingredients proportioning, and then we will find out in the ingredients, fibers takes a good important part. And always we say we have to have good construction practices, good consolidation, and good curing in our concretes. Okay, so we go back to cracks. We know that concrete is very good in compression, but not so good in tensile tension. And therefore, it's a brittle material, like a piece of chalk. So when you load it and you bend it, you get cracks. So this is from our former VDOT state materials engineer, Charlie Robson. And Charlie Robson in our meetings would always tell us there are two kinds of concrete, one cracked and one about to crack. And he's correct. He's correct. Concrete will crack. So the key is we want to control those cracks. We want to keep those cracks very tight and very few type of. Can we do that? Yes, we are able to do that. So when does the crack occur? The crack can occur at the early stage or at a later stage. Okay. So here is an early stage cracking, plastic shrinkage crack. And what happens in the system is that when concrete is plastic, meaning it's not hardened, it has not hardened, it's not started gaining strength. What happens is that as the water evaporates from the surface starts becoming dry, but inside is still wet. So bleed water comes in, but bleed water may not bring enough moisture to the surface to keep the surface wet. So we say when the rate of bleeding, when the rate of exceeding, rate of evaporation exceeds the rate of bleeding, meaning that the surface can stay dry, then you start getting these cracks. So what do? You don't want the surface to get dry. We do proper curing. What is proper curing? We mist it or cover it immediately so the surface doesn't dry out. Another thing is the later age cracks. These can be because of loading, like in this case, the negative moment area. This is over the pier, or it can be because of drying shrinkage. As the water is lost over the weeks and months, then you can have some transverse cracks in the system. So the cracks do occur. Now, what do we do? How do people address these cracks? One effective way is to use fibers. And a lot of people use these synthetic fibers in very low amounts, 1.5 pounds per cubic yard, which is 0.1% by volume. And that is to prevent plastic shrinkage cracks. And what the fibers really do is they don't let the water be lost from the concrete easily. They go and close the channels that the water is running out of the concrete. So they are effective, it works. But we say that we like in VDOT use curing processes rather than use low amounts of synthetic fibers to prevent these cracks. Another thing is that the later age cracks. Later age cracks could be, as we said, drying shrinkage or load-related cracks. So for those, we need to use large amounts of fibers and certain types of fibers. When I say large amount, I'm talking about 2% by volume. Look at 0.1% by volume for the plastic shrinkage, but for the hardened concrete, we are talking about 2% by volume, much higher and also much stronger fibers. Here are some of the fibers that we have been using. Some of them, as you see, here is the synthetic fibers on the top. The very left is the polyvinyl alcohol fiber, and we'll talk a little bit about that. We use that in what we call engineered cementitious composite, and the polypropylene, nylon. These are the synthetic fibers available. And then at the bottom, you have the metal fibers. The very left one is the brass-coated steel fibers that is obtained from the steel belted tires. They chop those tires, and that's what is used in the ultra-high performance cars. They are very highly efficient fibers. And then we also have these hooked end fibers, as you see here in the middle and the right, lower fiber pictures. And it can be loose, like you see in the middle, or it can be glued together. The longer fiber, we like to use glue, because if you don't use glue, but use it loose fibers, they tangle, and then it's hard to separate them by mixing type. So glued it makes dispersion of these fibers much easier. This is something very interesting and important figure for you. And if we understand this, it helps us a lot about the fiber reinforced concrete. Here in the very left, as you see, no fiber. And no fiber means that just the plain concrete. In the plain concrete, if you use a flexure test, meaning that you could apply lateral loads like you see on the top there. And what you will find out that if there's no fiber, when you have a certain load and certain deflection, very minute deflection, it separates into two. You get two pieces, like you say, no fiber, two pieces at the very low. Then you put a little bit fiber. Then what you do is that after it cracks, like a 4,000-pound load, it cracks. After it cracks, it comes down and still provides you some carrying ability, as you see. A white crack occurs. Here you have two pieces, here you have a white crack occurring. But what we are interested in is the one on the top, which is shown as deflection hardening system. And what you see there is that because of the fibers, the concrete at that location, crack location, becomes stronger because the fibers come to your aid. The fibers are carrying the load, and the fibers are very, very strong. Okay, so that's the deflection hardening. And when you do that, the crack, when it occurs, doesn't get wider because it's very strong in that region. So what happens? You get another crack next to it. And as you see in that picture, you have multiple tight cracks in the concrete. So that's, yes, please.
So when you're mixing up and you've got these fibers, right? They're kind of, they're just in the mixture and they're randomly.
In the mix, yeah.
How does that mesh with the glued?
Oh, the glued fibers you are talking
Does it
about?
have to be manually set?
The glued fiber in the water soluble glue. So when you add it into the mixer, when you mix, it just it does a dispersion. Because if you put loose, then loose tangle, and it's very difficult to separate them. But glued appears to be well dispersed in the system. Separate from each other because of it. Very good. Thank you so much. So please try to remember this. Based on the fiber, you get some residual strength. After the crack, you still have some carrying capacity, but the level of the carrying capacity depends on what type of fiber and how much we use those fibers. Okay, so we then say that to control cracks, we can use fiber reinforced concrete. The fiber reinforced concrete not only helps you with the ductility and having residual strength, also gives you higher tensile strength because fibers are like minute reinforcement in the system. So they improve your tensile and flexural strength. So that's one of the advantages. And the other advantage is that it provides you some ductility in the system. Now, today I will spend more time on high performance fiber reinforced concrete that deflection harden. When we say deflection hardening, it means that after the first crack, it is stronger. The first crack meaning that the concrete cracks. When the concrete cracks, the fiber starts carrying the load, okay? And the fiber is much stronger than the concrete. So that we say if it is a higher load carrying capacity after the first crack, then we talk about deflection hardening in the system, okay? Thank you. So if something is confusing, please ask so that I explain it more. Now, we will talk about three types that we use in VIDA. One is the engineered cementitious composite. And Mir will spend more time explaining how we fix culverts with this type of concrete. And then the other one is very high performance concrete, and I'll tell you where we use that concrete. And the next one is the ultra high performance concrete. This ultra high performance concrete has very high strength. It is by definition compressive strength of 17,000 psi or more. In bridge decks, we use 4,000 psi concrete. This ultra high performance 17,000 psi minimum. And then the very high performance concrete is 11,500. So these are very strong concretes, and they also have fibers in them, and the fibers also make them a highly ductile system. So they are very powerful, and we use them in some applications that I will explain to you. Now, ECC, the first one that we are talking about, the engineer cemented composite, is also known as bendable concrete. And look at this now. This is here the concrete. Wow. Bendable concrete. Now it's difficult for you to see maybe, but there are a lot of tiny cracks. But look at it. If it was a regular concrete, when I load it, it will never be like that. It will just break into two pieces. Yes.
How much of a load approximately is that?
How much load can we tell? Like we are getting, when we talk about these systems, we talk about splitting tensile strength and flexural strength. So here is the flexural strength. We can easily get 2,000 psi flexural strength out of it. Regular concretes are more like 400, around 400. This is 2,000 psi flexural strength. So these are very powerful. And then the VHPC is close to it, maybe 1,700, 1,800, the VHPC system. So these are very high quality systems, and we have these systems in VDOT right now. So again, look at the bendable concrete that I showed you in the machine. When you look at it, I forgot to bring my sample. Maybe next time when we get together, I'll bring the sample, actual sample. You will see these. As you see, when you look at the slide, look at how much gold it has in it. And then if you look at the bottom, I don't know how clear it is. Can you see the many tight cracks? So rather than one large crack that you would expect with a lower amount of fiber, you have multiple very tight cracks in the system. And it's very difficult to penetrate through these very tight cracks in the system. Now, let's look at some of the applications. Where did VDOT use these things, for example? In the ECC engineer cemented company, we use it in shear keys. As you see what a shear key is, when you have two slabs, usually voided slab, you have a shear key, as you see, a shear, okay? That's blue there. And we have used it in link slabs and culvert repairs. Culvert repairs, Mary will tell you more about that. So they use in the system PVA fibers, very special fibers. It comes from Japan. It is a very good fiber, synthetic fiber. We use about 40 pounds per cubic yard in this. Look how much it is, 40 pounds. With the other, for plastic shrinkage, we'll talk about 1.5 pounds. You know, we're talking about 40 pounds of fiber. Now, let's see some of these applications. For example, we did this in 2013, our first application about 10 years ago in Route 645 near Winchester. This thing is this small bridge we used. This is during construction. As you see here, we are filling these shear keys with some different things, and one of them was the ECC. And what we found out that it didn't leak, it did well. So now VDOT is using this in shear keys. Then let's look at the link slabs. This is a I-64 bridge, Dunlap Creek near Covington, this bridge. And we used here ECC in the link slabs. So what is this link slab? Is you see the joint, and joints are always a problem in the bridges. Okay, so we try to eliminate that. So what do? We come in and take out the concrete on both sides of the joint, and we put reinforcement, and then we place our concrete. Even though you put this reinforcement under normal conditions, you will have some cracks, usually cracks in the direction of the travel. You will have these cracks. So what we do, we then try to put some fiber ECC system. And look at it. Look at the crack, 0.1 millimeter, is it? And he is trying to find those cracks. Very tight. Okay, yes.
So he looking for these very small cracks, that's why he's on his hands and knees. and then you put a little bit of fiber reinforced concrete in it, or you put
No,
actually fibers in it?
The concrete, this concrete has the fibers in it. When we place it, it has the concrete, the fiber. But when it cracks, the concrete cracks, the fibers start holding the system together
Uh-huh.
because it is very strong.
So what is he looking for?
He's looking for, you see, there's a crack.
Oh, it's inspection.
Yeah.
Okay, I thought,
Yeah, yeah. No, this is, he's trying to figure out the cracks and how wide those cracks are. But as you told him, the cracks are very tight. There are many of them, but they're very tight. You have to be on your knees to see them. And those kind of tight cracks don't let solutions penetrate. And that's our, when we talk about the keeping dry concept. A culvert repair, and Mary will tell you more about culvert repair. We have been very successful with that. Now let's look at the VHPC, 11,500 with a splitting tensile strength minimum 1,400 PSI. Okay, where do we use it? Where we use it is that when we have the voided slab, what we are doing now is block out. As you see, top of the beam have like an L-shaped open spaces with the reinforcement coming from the beam, and then we tie them together. We put a bar there and put our high quality VHPC material in there. So it holds it together. Because in the old days, or in the past, what we did was when we had these 5, 6 of them next to each other, we have post tensioning to hold them together. But we found that it doesn't work. It leaks. So now we are doing this, what we call a Virginia adjacent member connection. VAMC, Virginia adjacent member connection. Okay, so that's what he's doing. Now he's putting our concrete in there. Here you will see 2 pictures on the left-hand side in a new construction we are using. We are putting together. So the question comes, if I want to widen, and how am I going to tie them together? You know, what am I going to do? So what we do for that is that we drill a hole here, cut it out, put a bar in there, and put our material in there. And we have this, for example, near Hampton. This picture was taken there. So we can use connect 2 slabs together by this VHPC concrete by this system. Okay, very efficient, and we are doing this a lot of these. Now, one other application of VHPC we are looking into. We have done some, as you see, mock-up is to fix the beam ends. Some states have started using ultra-high performance concrete to repair the ends of the beams, the corroded beams, and they are using their UHPs. But we think that very high performance concrete, which is much easier to make than ultra-high performance concrete, will be fine. So we are working on that, and we are very happy with the result. So we are hoping very soon to fix some ends of some of the beams, and one of them is near Charlottesville. Let's look at the UHPC. So what did VDOT do with UHPC, ultra high performance concrete, which is what everybody talks about these days. But what we are telling you is that we have other fiber reinforced concretes that does many good things and are easier to make than ultra high performance concrete. So when we have a problem, we don't run to ultra high performance. Okay, but does that mean VDOT doesn't use ultra high performance concrete? No, that's not true. This bridge, 2007, has 10 spans near Tappahannock. 10 spans, and one of the spans we put ultra high performance concrete. 5 beams there, all made with ultra high performance. So in 2007, so we have a good history with ultra high performance in the state.
The beam itself?
The 5 beam totally UHPC. Okay, and maybe we'll have opportunities to explain these projects in more detail in the future if you are all interested. Okay, so I'll be very happy to come and talk to you about this. So we have done that 2007, but today or recently we have been also doing some of the connections. You see, connected. This is the UHPC application here. What happens is that, excuse me, there's this lady.
Did anybody do a key to a Volkswagen?
yeah, maybe me.
It's you.
Me.
I'll bring it back.
Okay.
I turned it into administration.
I'm sorry for the interruption, but what we are talking about is that when we are connecting and there are reinforcements coming from both sides of this structure, it is very important that you have very short splices. and you have very short splices, like maybe here 4 inches, 5 inches, short splices, like in the blackout short splices, we need high tensile strength. Regular concrete won't do that, okay? So that's when we go to VHBCs or UHBC type of system, okay? UHBC is harder to make. VHBC is easier to make, and VHBC is very close to UHBC. So we in Virginia use more of VHBC than UHBC. So in conclusion, I hope I didn't take too much time carrying this information. Conclusion is that fibers are effective in controlling cracking, and low amount of fibers are used for early age cracking. Some people, but we prefer good curing practices. High amount of PVA and steel fibers, when I say high amount, 2%, whereas the other one is like 0.1%. Steel fibers are used for long-term and load-related. Very effective. As you see, if we have the right concrete, we can keep those cracks very tight. There will be cracks, but very tight cracks, difficult to penetrate into. And based on type and amount of fiber, tight crack can be easy. So this is the presentation. And thank you for the opportunity. And I think, can we have some questions now or later?
Just make sure that Mary. can-
Okay, Mary has made the presentation. I didn't take Mary's time, did I?
No, any time is just about right.
Yeah.
Thank you. Mary, you can come on up. I will,
Very good. Thank you. Oh, what did I do, Mary?
walk away.
What did I do?
Yes. So I want to introduce our next speaker. Thank you very much, Celik. I enjoyed hearing that. I haven't seen you in many years, so I enjoyed seeing
Oh,
you.
well,
again.
yeah, thank you.
Our
You learned
next-
something too? You learned
Yes.
something?
I remember. Our next speaker is Mary Sharifi. She is a research scientist at VTRC. She has a Master of Engineering degree from UVA. And at VTRC, she specializes in concrete characteristics and issues, bridge decks and overlays, and sustainability issues. And we'll let Mary take it away.
Thank you. Thank you for the opportunity. Good afternoon, everyone. I'm going to talk about the one of the application of FRCs, which is repairing of the steel culvert with sprayable fiber reinforced concrete. There are so many culverts in Virginia that they are subjected to corrosion and abrasion, mainly in the inverts of the culvert. And we know that the replacing of the concrete culverts are expensive and also requires to temporary closure of the affected roadways. So we were thinking about various types and repair methods. And there are slip lining, cured in place pipe liner, invert lining with cement tissue materials, and spring casting. And with the slip lining, it involves inserting a pipe liner into the directly into the culvert, and the diameter of the pipe should be smaller, so we might have some water flow reduction, and it's not good and may cause concerns from hydrologists or environmentalists. And also curing space that involves the insertion of a thread or fiber tube saturated with resin. And this is again in kind of new chemicals that may cause some problem environmental. And there are some concrete repair methods, and one of them is spin casting, with spraying cementitious material to cover the inside, and also invert lining, which you can pour concrete in the worn area, but the thickness of the culvert concrete will be 4 inch, and this thickness can cause some hydrological problem, and also since there is concrete, and you can have some conventional concrete, so you can see the cracks, and it can cause the infiltration of water and solution into the culvert.
Mary, can you speak a little louder for our
Sure.
audience, or maybe even a little closer to the?
Yes, sure. So in our innovative method, we are using fiber reinforced concrete to reduce the thickness of the concrete to 1 inch, and also using of fibers helps to reduce the crack width, and with the ECC, for example, we can have 1 inch thickness of the concrete in the bottom of the culvert, and also this can cause less environmental and hydrological problem. And the typical ECC, as you can see, we have so much fine content like fly ash, and also we have a special kind of mortar sand in our mix design, and 1.5 to 2% by volume fibers, PBA fibers, and that can help to reduce the width of the crack. And in our for the first investigation, we did some demos in our lab, and we prepared the ECCs, and we put for the reinforcement, we put geogrids in the invert of the culvert, and we poured the ECC. We took samples, and we saw that the flexural and tensile strengths are very high and good. So we had so many little tight cracks, and so we decided to try it one more time in one of the districts, and we again we had a good results. And the geogrid and spacers at the invert can help to strengthen the structure and also keep concrete in place, and attach ECC to metal pipe, and those spacers can ensure us to have a thickness of 1 inch of concrete. And so we had a good results from our trials, and then we decided to implement our research into the job, and the first field application in 2017, we went to Lynchburg district, and there was a culvert with 70 feet long dimension, and we tried to just select this first 6 feet section. It was asphalt coated, and but still we put the geogrids and poured the concrete, and even after heavy flooding at that time, we went to inspect it, and we saw that the concrete was in place, and we had no problem in the in that implementation. We did the manual placement and concrete made in the mortar mixer, and we took concrete from the mixer with the bucket, and we did the manually, and it was a satisfactory work. And then we decided to try more of the repair, and we tried in Lynchburg and Richmond districts, and we repaired all of these concrete culverts, and you can see the type and the length was varied between 51 to 84 feet long, and the height of the concrete, the culvert was from 5.8 to 10, so it was easy for people to go inside the culvert and spray the culvert and the concrete, and so it doesn't take that much preparation before, maybe a day or 2 days before. You should just go and divert the water and clean the culvert and put the geogrids and the spacers, and then the day after, the ECC was prepared in a truck mixer in the plant, ready mix concrete plant, and the fibers were added manually, PBA fibers, and with the help of the trailer pump, we could, and the help of the state forces, we could spray the ECC into the culvert easily. And this is the shotcrete nozzle, and that tube is an air pressure.
That's a question about when he was applying it, because that was a little down in the photo. So to apply it, does he need any breathing, anything?
No,
or-
it was not. Maybe he was just trying to, because the height of the culvert was at least 5.1 feet, so it was not that hard to get into there and breathing. And the length of the culvert is
But with the spraying, there's nothing that gets airborne or anything. that you
no,
need to
not
check.
not that much. No, it was not a concern. And here, with the help of the state forces, they spread the nozzle and the culvert in 1 or 2 hours, and they finished it. And you can see the finish, very smooth finish. And there are 2 levels of consistency for the ECC. We can make ECC as a self-consolidating concrete. The slump flow can be between 18 to 21 inch here. It's better for manual placement because it's easier to place the concrete. And then we have a consistency of a stiff mixture. The slump should be 1 to 3 inch, and it is good for spraying. Actually, the pump operators, they asked us for having a more stiff mixture. It's easier to disperse the fibers and also easier to spray the PCC. And the problem with the wet mixture is that the concrete, if you can see, there are some clumps of concrete. It was sliding down the sides, so it's better to have a stiff mixture. And when we have a stiff mixture, we have to have some vibrator that helps the concrete come down to the grades. And then all of these culverts were being surveyed by district maintenance team, and they after all of them had experiencing the flooding, but after that flooding there were no problem, and the general condition of the ratings of these culverts were from poor at first, and then after repair it came up to the good condition. And now we are trying to find some to make some modification to our ECC mixtures to have a better consistency, not too wet and not too stiff, and we need to have a very good fiber dispersion. And we would like to get rid of those geogrids because of the cost, and also the preparation of the culvert will be easier than putting the geogrids on. So if we want to get rid of those geogrids, we need a better stiff mixture and better fiber distribution to help the reinforcing. So in the lab now, we are trying to mix stiff and sticky mixtures. If we can do that, and if we get some good mix design, then we can be able to even fix the whole entire interior culvert. And we mix a fiber, mix a ECC, and then have some handful of the culvert concrete, and then we throw it toward the wall to see if like a demo for the spraying and shotcreting, to see if it sticks into the wall or not. And for now we are getting there, and I think it's not sliding down from this wall. And for having a very good fiber distribution, we are looking for some better mixers. Here is a very high shear mixers with which are these are for other applications for VHPC and UHPC, but we are thinking about having these kind of mixers for our result. And also here there is another high shear mix, pan mixer, and this one is very efficient. We can have a better fiber distribution here as well. And for conclusion, we can say that ECC can be used in culvert repair successfully, and it was successful. And we can put ECC in thickness of 1 inch or less. Fibers keep the crack tight, and also ECC has high tensile and flexural strength, ductility, and very low permeability, and because of those tight cracks. And we can repair the entire interior culvert repair, which can help with the structural improvement as well. With that, I would like to thank you again, and I'm happy to answer your question.
Well, round of applause for our speakers. Thank you.
Question.
Yeah, I don't want to get in the way of the audience. I'll stand over here so the remote audience can hear us for now. Any questions right now from the remote audience?
When you were doing the invert repair,
Right.
where the invert repair stops in the original culvert crown.
Right.
At that joint. In your long-term studies, did you see deterioration happening there? Where the invert, the repair stopped in
In
the
the
original
joint.
pipe, yeah. You see any issue there?
We didn't see any issue.
Not any problems. We have been doing this since 2007.
Yeah.
So we have 6 years of experience. We haven't seen anything like that. Plus, when we repair, we are inverts ends in a solid area, so no problem area.
I'm just curious, like,
So,
doing this-
no, not we haven't heard any problem. Now, the beauty of this system versus the conventional system that we are doing as well. For example, there's a geogrid, geopolymer material, geopolymer material that they are trying to use. But those materials do not have the fibers, high amount of fiber that keeps the crack tight. So the issue is this, is cracking a problem in the culvert? We feel that anytime you have wide cracks, that means water can get in there and accelerate the corrosion process in those areas. And it can work up and down. So our goal has always been try to keep the cracks tight. So what do you all feel? Do you think that we should keep the cracks tight?
Yeah,
Well,
I would agree for sure.
yeah, that's what, because I look at a recent design with the geopolymers, they were talking about cracks from 0.3 millimeter to something like 1.1 millimeter type. So those are pretty wide cracks. I don't think it will penetrate easily into those cracks. That we are trying to eliminate them. We are trying to make sure that this color, this layer is very tight. And it is like another culvert inside a culvert, a solid piece. So that's our goal.
And you've only used it on corrugated metal pipes.
So far, we have done it on corrugated. Yes, but we can definitely use, the good news is that the concrete pipes seem to be doing well in the country. So they are not telling us that, I think the problem there is usually the corners.
Yeah.
So we don't know, if they want us, we can definitely look and see what we can do with our fiber system, this bendable system in those areas. But right now, there are over 1,000 corrugated metal
Galvanizes.
galvanized corrugated metal pipes that need in repair. So we are trying to make, like, this is so easy that our state forces can do this. You know, all they do is buy the material. Our problem has been to make the ECC in the truck. This is our challenge. But we are working on it. We are trying to improve that and to be able to do that. And I think we are taking we are getting that. So it takes time, but I think we will get that. So that's our goal.
Let me ask the remote audience, if you have a question, you can either type it in the chat or you can unmute and ask it. So let me just give them a chance
Sure.
and we'll give a few seconds.
Hey,
That's good.
Karen.
One question from a remote audience.
Yes,
ahead.
we do have a question that someone sent me. For Mary, the culverts with fiber reinforced concrete from poor to good condition, which, and they've lasted a long time, which are both great things. How does the cost of this solution compare to others?
The cost is
Okay,
very
go
low,
ahead, go ahead.
isn't it? The cost is
cheaper.
much cheaper,
Yeah.
yeah.
Because first of all, we are doing this, but the
Because state
state
force.
also we have done all these column repairs. So cheap compared to what you would go and contract.
Just making
You
the
know?
ECC in the concrete plant and fiber, PVA fiber.
Yeah,
Mm.
no,
The
if you
material
look at the
cost is
cost
really
of the material, this material costs more than the regular concrete, like a three-tech concrete, because the fibers are pretty expensive. A bag of fiber may cost $300, $400 that you put into this 1 cubic yard. But all we use 2 to 6 cubic yards of concrete in these columns. So it is not a big deal. The mobilization to going there and trying to do these things is what takes most of the expense is related to. But we have figured that at that time I have calculated one of these fibers where we were doing it like within thinking about the time of the people, something like $20,000. We were able to fix a color. Whereas if you were to go out and do it, probably it would be 100,000 or more fiber to fix a color. You know, so definitely, the price, the cost is much lower, but the issue is that we have manpower issues, like any other industry, that's right. So, can the state forces have the time to do, so we are working on that. We are trying to make it so as simple as possible, like we are trying to get rid of the joke, so that it sticks on its own, yeah.
So are these still research projects only, or is there
No, we want to
approved
be,
material?
so we already have this going.
Okay.
The research project is to improve on what's being done. So there is, right now, you want to repair a culvert, we are there, we can do it. Culvert repair right now is possible. And as I told you, we have done 8 of them, and no complaints, no complaints. You know that, in fact, the first one we did, we should have asphalt lining. You know that concrete doesn't bond to asphalt that well. So, I asked them, in our meeting, I asked them, can you please remove this asphalt coating so we repair the injury? They said it's cheaper to replace the whole culvert people at that time. So they didn't want to get into cleaning the asphalt or replacing the asphalt. Okay, we said that, okay, then we'll go and put it in. So we put it in a 6-foot section, like Mary was explaining, and then the question came, is it working? So few months later, they told, we were talking about how are we gonna know if it's working or not. What I told them is that take a hammer and bang on it. If it sits there, it stays there. So, well, 6 years back, it's still there. So what should I worry about, you know? It's still there, it's functioning, it's doing its job. That's the key thing, right? It has to be performing well, and it's performing well so far. And the good news is that we have done most of them in Lynchburg. That means that people are comfortable. I don't know whether you know the people, but Todd Moore is a wonderful engineer there that has given us this opportunity to do this work.
And the time of the repair, within 2 hours, the spraying. will
Yeah,
be
spraying,
finished.
when we get there,
Yeah.
we, just the spraying part, in 1 hour, probably within.
It's just
an
like
hour.
concrete,
Yeah,
right?
yeah.
Just like when you do a mold, you just start the thing,
And if you look
load
at
it a little bit. you're done.
we didn't even have a special shotcrete operator, the state force, because the first time the pump came there, and then we asked the pump operator to spray it. He said, he cannot do it. No, I mean, the shower, I mean, this is a private company, that broke the pump, the weekend, they didn't have it. So they said, we cannot do it. So what happened? One of our people come, who had never done a shotcrete job. So what I'm trying to say is that anybody who has a problem, I can do it. It's fun, right, you know? So it's a very simple operation, very simple operation.
Take good weather and not have to coffer dam it.
Yeah,
Yeah,
and
yeah.
for diversion of the.
You
water.
know, with the weather.
You see, you are always in the public, so it's always nice. The problem is that you don't want water in there, right, spraying this, so
Yeah.
for that, and then the other issue is that most of these houses, they hold.
Yep.
So we try to put some kind of rapid setting cement, and some people say that there's water stopper type of, you don't want the water to keep on coming out type of thing, mixed with this, concrete, because it would weaken the concrete. So we try to, this is still coming a little bit, but not much to a degree that it washes away the water. So we tell them, go ahead and put some rapid setting cement in those holes. And so far, we've been pretty successful with it, and we definitely like to do more. We definitely like.
I think you definitely have something with the joint repair as well for the concrete pipe, because when you have
Yeah,
somebody put it in wrong
Yeah,
and
we did not
you
get
have
it.
joint separation.
yeah,
We've done the
Yeah.
CIPP before.
Yeah.
I'm just curious, like, what are the environmental
Okay.
concerns at CIPP that you had?
No, we did not get into the concrete repair joint and this and that, because it looked like that either there's not a need or the need is not a top priority in that area. So their biggest thing is now to fix these metal culverts, because as I told you,
Yeah,
there are
lots
holes at the bottom. There are holes at the bottom. And sometimes people worry that if it is a lot of holes in it, it may cave in.
Right.
You know, so they worry these things, you know? So we are trying to now fix these things before they come to the stage that we have to replace. So we are there. So we will see how the lead up will approach this, but definitely we are trying to encourage them to use more of this material. The beauty about this material is that in very thin sections, like you understand, 1 inch is about the corrugation is what you have to do.
That's
One
amazing.
inch about the corrugation. And you don't need to do a welded wire or anything like like that because the fiber itself provides the all the reinforcement.
If it's just on instant, you get your fish passage and stuff.
Yeah, the environmental, all that.
Hi, John.
Even if you can't go to 2 inches, they're not gonna, I think, to worry about it, but definitely we want to stay within that inch. And all these eight ones with a 6-year history, seems to be doing well, functioning. So hopefully you all will find some that we can work together.
I want to see if the remote audience has any more
Oh,
questions.
sorry.
We have, no, so we have about 2 minutes left, so I just want to give them one more chance.
Oh, I didn't know that was a clock.
Oh,
I just realized it myself. We just noticed the clock in the back of the room, rather small. We'll just give it a few more seconds from the remote audience. Again, you can unmute yourself, or you can type it in the chat.
We do have one more, Karen.
Well,
Are the synthetic or steel fibers used in the reinforced concrete, are any of them ever obtained from recycled materials? And if so, do you think it's an amount enough to be effective use of recycled plastic or other materials?
I think that the question is, these fibers we are using, are they from recycled materials? I think that, and I really don't know, but what I know is this, the fiber that we are using, domestic, the steel fibers. The synthetic fibers came from Japan. They were the PVA, polyvinyl alcohol fibers, because they are very special fibers. They have an oil coating on those fibers, because you don't want the fiber break. If the fiber breaks, the crack widens. So you want it to pull out of the system to release energy type of thing. So it is a very special fiber, the PVA fiber we are using. So it came from Japan. So I don't know whether they are using it from the recycled materials or not. The steel that we use is very common, those steel fibers, domestic fibers we try to use, and they are using a lot of those hooked end fibers in tunnel linings, like in buildings and tunnel lines, like hooked end fibers. So all these fibers are domestic. We have to use Buy America is very important for VIDA. But I am not sure whether the manufacturers are using recycled material for those. We are not sure about that. Definitely, we like to look at the carbon footprints and sustainability. These are big things for us nowadays. But we feel that we have been doing those things by using, for example, supplementary cementitious materials like glass fly ashes and things like that, which is this mix that the ECC mix has more fly ash in it than Portland cement. Type of thing, like maybe 10–15% more of it. So our goal is to use supplementary cementitious byproducts, and our also goal is to make more durable concrete, because we feel that durability is a part of sustainability. Something durable is a sustainable system. So those are the things we are interested in. And also one other thing we are doing in VIDA is trying to use maximum total cementitious materials, not minimums. Like our low shrinkage bridge deck concrete have a maximum cementitious material, 600. So that is another thing, pushing people to use lower cementitious materials, especially the Portland cement, which is one of the highest carbon contributing material. But when you look at the concrete, it is one of the better materials in terms of carbon footprint. So that's the sustainability.
All right, well, our clock says 1:01 in the room. So I want to thank everyone for participating in our third Lunch and Learn, and for our 2 speakers for traveling, and for, I really like the pictures, I like the questions and answers. So thank you so much. And Taryn, I think we'll be ending the meeting. I think if you are willing, we can send out your emails to all of our people who registered in person and remote, so they can also contact you later.
Definitely. If
Thank
you
you.
Google my name, you'll find.
Thank you. Again, round of applause. Thank you so much, Celik and Mary. All right.
Thank you so much.
Thank
And
you.
through me, you can be married. And it was fun. Thank you very much for the opportunity.
Thank you.
Our problem is we want to say so much, but we have so little time. So hopefully, if there is interest in some of these topics in more detail, I hope Karen can arrange some more meetings for all of us and talk about in more detail. Thank you so much.
Thank you so much.
We really appreciate that. Karen, thanks again.
Thank you. Well, I think my